I'm going to give you a little bit of an overview of GraphQL at Brigade and what it's done for us, what our experience has been like adopting it, and some of the things that we've learned along the way. So we've been using GraphQL in production for a year or so. We're using it across our web apps, our Android apps, and our iOS clients, and it serves 100% of our data requests. We don't have a huge team, so the benefits that GraphQL has given us have really made a big difference in our ability to move quickly and execute well. We've learned a lot. I'm excited to share some of that with you today. So I'm Steve Rice. I'm a software engineer at Brigade. I'm focused on backend and our APIs. And I've been there from before we had GraphQL all the way through us starting it, bringing it into production. So I've seen a lot of how it's evolved over time. I'm going to cover most of Brigade's journey with GraphQL, and there's a lot going on there. So if something is of interest to you, please come talk to me after the break or anything after like that, and I'd love to talk more about any of this in depth. I'll start with what Brigade is, how we came to use GraphQL, how GraphQL has impacted our development workflow and tools, discuss what we deal with running GraphQL in production, and end up with some of our kind of key takeaways from this journey. So Brigade's vision is a highly participatory democracy in which voters, instead of donors, hold the true source of power. So we're a company that's focused on restoring the feedback loop that exists in a healthy democracy between representatives and their constituents by getting more voters to be engaged so that we combat sort of the influence of money in politics with direct engagement from constituents to their politicians. So we do this through a variety of features, things that are kind of aimed at being a companion for a user's civic life. A Brigade user can use the platform to take action directed at their representatives. She can organize with other like-minded voters and hold her representatives accountable. So you can see three of example features here. Our petition experience, where constituents can tell their representatives what they want them to do. Brigades, where organizers can kind of recruit others and organize them around a political cause. And the rep tracker, which allows users to follow up on what their representatives are actually doing so they can go to the ballot box making an informed decision about whether their representatives are actually representing them. So all of these features are drawing from a lot of different data sources. And what we want to do is just provide our users with a pretty straightforward and hopefully delightful experience. So we have an architecture to do that looks a little bit something like this. We have a few different clients, so web client, Android, iOS, as I mentioned, even a web server that's doing some of our server-side stuff. And they all communicate with a fleet of different microservices, and this is managed by our GraphQL layer. So our requests come in through Kong, which does authentication, attachment, other HTTP level like normalization concerns, but then it performs the network level routing and hands everything off to GraphQL to do all of the data management. GraphQL is then providing everything with a single, consistent interface in such a way that clients don't have to worry about which API am I talking to, what protocol does this service speak, how does this service differ from other services. But of course, it wasn't always this way. So in 2016, as the election season was kind of picking up, it was really highlighting some of the issues that we've been seeing previously, supporting multiple clients that show different experiences of a lot of these like data-rich kind of product features. So we had a monolithic application that was serving our single internal Rails API. Pretty standard tech. We're doing RESTful API calls. We're serving JSON over HTTP. We're using active model serializers, which some people may be familiar with, to actually turn our data into JSON. And what we were finding is we were doing a lot of expensive stuff to serialize our API responses. So like if we want to have a single response for our client, which we do, so they're not making expensive round trips, we have to provide everything that they need inside the payload. And so this means a lot of like nesting of objects kind of arbitrarily deeply in our JSON payloads. So for instance, we have positions that users can take. Those users have profiles. They can be responded to by other users who also have profiles. Then users can explain those responses, and those users also have profiles, and then comments that also have profiles. You can see where I'm going. And so like an object like profile is just all over the place in our response. Not only is this a big response, but we're duplicating the data kind of all over the place. And this gets expensive for us to even just take what we've built up as a query response and convert it to a JSON string. So we have to do things to mitigate this. So we'll do things like once we get to a certain point, a certain depth in this response, just stop serializing things that have already been serialized 10 times already. But now clients have to worry about, well, when I look at a profile, is it going to look like a profile, or is it going to look like something that has a bunch of null fields because we didn't serialize all of it? So now we're doing null checks everywhere in our clients. Not great. And of course, we have versions in our API so that we can support multiple backwards compatible versions. But that's really tough to maintain, especially if you're trying to do something internal. We just want to kind of move fast. So we have an edge version or sort of like our own infinite version. And now we're back to, OK, every time we make a little API change to support a new feature, it breaks a different client that we didn't realize would break. With many problems comes plenty of bike shedding about how to fix them. And so we have to kind of go through this whole API proposal every time we want to make a change, get sign-off from all the key stakeholders, and really becomes this process-heavy thing just to like build a new feature on our API. So to address sort of the serialization needs, we looked at kind of just flattening our API responses where we could reference things somewhere within the API response and then just kind of provide that object later. So clients still don't have to make more than one request. But there's no like tooling for us to use to put this kind of thing together. We'd have to build it ourselves. And clients are still going to need to go through and figure out, OK, now that I have this profile object, where am I going to put it in this tree of data? So we kind of gave up on this strategy. We looked at JSON API as a solution. Nice thing about that is clients can kind of just query for exactly what they want, since everything has an endpoint that you can hit to just get the data. And of course, we also looked at GraphQL. So clients wanted to just be able to define, here's what I want from the back end. JSON API gives them one way to do that, but GraphQL even more so. When we were comparing the two, GraphQL just kind of gave us more of everything we were looking for. So we could completely eliminate overfetching. We could stay with just a single client request. And we have a real type system, so we could do all the schema validation, all the kinds of great tooling that we can build around something that has that sort of structure. Not only that, but like the clear laundry list of benefits made it easy for us to sell this to our client teams, our server teams, and of course, management, who had to give us the leeway to build this. So how do we actually start on a project like this? For us, it was key to just sort of start off small. We chose a single page in our admin interface to move over to GraphQL, something that users aren't going to see. If it goes down or there's some problem with it, we have some kind of fallback for it. Just get something deployed that we could get a feel for how GraphQL was working in production. Since we had this Rails monolith, the temptation was, OK, well, we've got a bunch of Ruby engineers. Let's write this in Ruby. But the Ruby library we found didn't really map to the way that we thought about data, in that it wanted types to kind of map directly to active record models, and we had a lot of logic in like service classes or in our controllers that were doing more than just here's the row in the database. We also have things that aren't backed by a row in the database, so it's hard to kind of build that kind of abstraction around them. At the same time, we're building a lot more microservices, so we need some sort of coordinator that can handle the communication between the services and also between our clients and the services themselves. So GraphQL seemed to really fit this bill well. If it was a new lightweight service, then it would be able to handle all these responsibilities. Node was what we chose because the tooling is the most mature in the GraphQL space. It's the quickest way to get started. The event-driven execution model, where some request gets fired off and we don't have to do anything about it until it comes back, really works well for GraphQL. And if you had to pick a language that everybody in your organization is going to be familiar with, you might not find one, but JavaScript's going to be the closest thing. So we set up this structure where our clients could start talking to GraphQL, continue talking to our HTTP API, and sort of just go to both depending on what data they needed. And we'd slowly transition things over from our REST API into GraphQL. And as we add more and more things to GraphQL, it's more and more valuable for clients to be pulling data from there. So we can sort of move from 100% of data coming from the monolith to 100% of the data coming from GraphQL slowly over time. Even if this meant what GraphQL was doing is just forwarding that request onto the monolith and still pulling it from the REST API. On the client side, as I mentioned, we've got multiple client types that we need to support. But our web client was the most well-defined in terms of architecture, using React in a homegrown Flux architecture. So we wanted to find something that would fit best in web first. Apollo client was pretty new at the time. Relay was a more popular choice than it is today, so we went with Relay. But it also brought along a lot of opinions about schema design, which we figured were important. I guess we want to have opinions, and GraphQL, the spec, doesn't really tell you how to describe your schema or anything like that. While it gave us some things, it also kind of gave us a lot of baggage that we had to deal with later. Things like relay IDs, this concept of a node interface, and a viewer type. These are things that we sort of debated endlessly about sort of what they mean and how we use them in our schema. And in large part, those discussions sort of led to, well, we don't need those things, but we're kind of stuck with them at this point. It also made this learning curve that we already had getting up to GraphQL a little bit more tough because it was hard to tell where does GraphQL end and where does Relay begin, since it's trying to abstract all of those differences away from you. On our native clients, we were lucky enough that Apollo client was out for iOS. There was a beta version for Android. This almost immediately saved us a ton of work over our HTTP stack, where we were writing custom serializers for everything, and now we could just do code gen, and it's all there for us out of the box. So once we have everything, we're working with GraphQL in production. What's it actually like to build product in this GraphQL world? Well, let's take a look at what we were doing before. So traditionally, our clients kind of need a full API to build against in order to make significant progress on finishing their features. So this involves this proposal of what the API is going to look like. It involves kind of sign-off and deciding that that's okay, that it's going to do the right things. Then our server teams go and build the actual API endpoint. At that point, the client can build something. And then when we go to integrate the two, almost inevitably there's a bug that we find or an edge case that we didn't think about, or somebody misinterpreted the spec or something like that. So we end up doing a little bit of rework. In a GraphQL land, that agreement that we come to early on about how is this going to work is the schema. And not only is it way easier to write, you can just open up a pull request, as we've seen, it immediately is kind of this unambiguous technical agreement that's actually part of the functional stack, so we can't accidentally overlook it and do the wrong thing. At this point, we have client and server work totally decoupled because they've already agreed on what the schema looks like. So our server-side teams can build the APIs that are going to back it. Our clients can build the feature, and we can even provide stub data for that schema, so we can actually test out the feature, see that it's working, and do some QA before the server is even ready. Now, we found that having clients actually define that schema has been super useful to us because they know what they need better than the server teams do. And all the server teams need to be concerned about is just, well, is this something that we're going to be able to deliver? We kind of started off thinking that, well, like our previous APIs, there'd be an API team. This is kind of the back-end team that manages the schema, make sure it's performant and everything like that. But sort of tying what our data model looked like to what our schema looked like was this difficult conceptual problem, how do we think about graphs and what does a data model look like as a graph? But we realized that we were kind of missing the point. That one of the key advantages of GraphQL is that you can have your schema for your clients, you can have your services with their own APIs, and you have this resolver layer where everything can kind of work out and you can tie those two things together however you want. So by mirroring client needs directly, we give clients what they want, and they're not performing all their own logic to try to turn that into something they can use. So a simple example, if a client is trying to do something like have a Brigade user join a group on the platform because they've been invited to it, or if the leader of that group is trying to add that same user, we know on the back end that these are actually pretty much doing the same thing. We're creating a group membership record in order to represent that. But if we put different mutations in the schema that represent that, then now we have the flexibility to do things that are context specific. Like if we're trying to have a leader add somebody to their group, but they're not actually a leader, we can do something different with authorization. We can show them different error messages. If there's anything else that we want to have behave differently between those two experiences, that's mirrored in our schema. And with clients working on GraphQL, with our server teams working on GraphQL, with operations working on it, it's kind of this big shared asset for us. So there's a lot going on within that GraphQL server. Of course, we want everything to be fast and we want it to be understandable. So having some structure around this has really helped us, and I'll go through that quickly. So we've got the schema layer, which simply says, okay, what do things look like? What can I query for? We've got our resolvers that then figure out how do I turn the fields that were requested in the schema into a request that I can make to my backend services. And then we've got our model layer. And here we're kind of abstracting away the details of this particular API endpoint or this particular RPC call and just turning it all into a standard JavaScript interface that anything can call. The resolver doesn't need to worry about whether it's a microservice written in Ruby or in Node or in Scala or anything like that. Backing those are our services. This is kind of like the data sources that Jake was talking about, where we kind of have a one-to-one mapping between that and one of our microservices. It sort of knows about the universe of what that service does. And then the transport layer is just the actual nuts and bolts of how do we talk to those services. Is it HTTP? Is it Thrift? How do we manage those kinds of connections? It doesn't know the meaning about what's going over the wire, but just how do we send it? How do we receive it? How do we handle that data? So having these sort of discrete layers makes unit testing a lot easier. Because they all have a defined responsibility, we can mock out the things that we don't care to test and just test the things that we do. We also do some sort of like more end-to-end query testing, where we've built a testing framework where we can specify a schema, a query, some variables we want to send to it, and what we expect it to look like and what we expect it to happen. And by doing that, we're kind of validating continuously that we haven't broken any of those things. So in production, what's it actually like to run this service? Well, production is going to throw all sorts of challenges at you. So it's important that when you see a symptom, you can actually figure out what's going on. Because GraphQL is kind of asynchronous by nature, this can be tricky because you can't just follow a code path and see everything that's going on. But the structure that it provides lends itself well to tooling that helps you sort through things. So 3 key pieces to this puzzle: metrics, logs, and tracing. If you have all of these, it can help out with your visibility a lot. So we track metrics that we send to Datadog via statsd with counters every time a field is resolved. We call out to a service. We access a data loader. We also gauge things like how expensive do we expect this query to be via just static analysis before it gets run. How long did it take for the HTTP request to finish? How long did it take for the actual GraphQL execution to take place? And then by putting all this data together, we can look at things like, for instance, what fields in our schema are actually being used by clients? What deprecated fields are being used by clients? Which clients are the ones that are doing that? So we can identify those and resolve those issues. We also log every request, every error. We attach tracing identifiers to these logs so that we can follow them through our system. We make sure that all of our user data uses GraphQL variables so we can tell the difference between a query and user data and make sure we're not logging that. And on the errors front, it's a little bit trickier. GraphQL, because it's kind of sitting in between everything, it's really a focal point for errors. Errors coming from upstream services, errors coming from clients, errors in the code that we wrote in GraphQL itself. And so things that are like an error of the same type can mean very different things depending on where they came from. So we try to attach as much context about what's going on in the state of that execution as we can. And we're using GraphQL's context to kind of pass that stuff around. So stuff like what client is making this call, what service are we talking to, what operation are we performing, and then we try to make a guess as to whether that error type is something that comes from a client, like the query syntax was invalid, or whether it's something that came from a server, like we got a 500 or we got a 400 or something like that. Now, Apollo Engine gives us a lot of this kind of stuff that I've just been talking about, and I wish we had had Apollo Engine a year ago. It's a great place to get like high-level metrics, see traces of requests, see where errors are trending over time. We have daily reports that our on-call engineers can look at to kind of look for any latent issues that we haven't noticed yet. And it's also pushing its own metrics into Datadog, which we can then correlate with our own stats-D stuff. It's also nice if we break our own instrumentation that this stuff still works. One thing we look at a lot is query patterns. So because GraphQL is mostly just a simple orchestrator, it's not running a bunch of expensive code on its own. If we have any performance or load issues, they're usually because we're making requests in an inefficient way. This could be that we have a request to a service that's really slow. Could be that we're making a bunch of small, fast, but just numerous requests in order to fetch a set of data, or because the way that our request is going through is sort of misconfigured in terms of its fan-out or depth. And what I'm talking about there is that on the fan-out side, we're kind of talking about a service, moving the request to a bunch of other adjacent services, and then sort of waiting for them to come back. Whereas the request depth is more of we talk to service A, it talks to service B, that talks to service C, maybe if we're really unlucky, that talks to service A again. And that kind of introduces some uncertainty into how long a request is going to take. And also we can run into the situation where because the client is now specifying exactly what data it needs, maybe we didn't need the data from service B, maybe we didn't need the data from service C, but service A doesn't know that. And so we're performing expensive operations to figure that out. So at Brigade, we've kind of stuck to this design principle where we limit our depth to just one, and we don't have our microservices talk to each other. Of course, they do need to share some data, but they can do that asynchronously via our queued event bus. All of our synchronous communication is just orchestrated through GraphQL. So it fetches what's needed. It doesn't fetch anything else that we don't need. And we avoid recreating kind of the problem of nested objects of arbitrary depth and just have it be nested services of arbitrary depth. Maybe this is a bit extreme, and we've definitely faced challenge in this approach. Sometimes it's tough to figure out, like, if service A really needs to get something from service B, how do we make that work? But it has kept kind of us from having any bottlenecks in GraphQL and given us predictable response times. So I want to look quickly at how we can pull kind of our monitoring together to investigate a production issue that we might see in GraphQL. So we start with an alert. We try to set our alerts to kind of cover any sort of novel or unexpected behavior in our system. So in this case, we got an alert that GraphQL is making a bunch of RPC requests to one of our microservices that we never expected to make that many. If we look in our overall metrics, we can see that the call volume has this spikiness that we weren't seeing before, and that it is the RPC we were alerted about. When we come into Engine, we can take the field that's resolving that RPC, find out what operations are actually resolving that field, and then pull out a trace from one of them, grab a request identifier from it, and go over to our logs where we can look at what's going on with that request and see that we're actually making 24 calls on the same RPC just to resolve that one GraphQL request, more than we'd expect or like. Finally, having the client information in Datadog lets us kind of zoom back out and see that this is being used by our newest Android and iOS versions, and also it seems to map pretty nicely to when we release those to the App Store. So what would I like to tell 2016 Brigade about what we know now in 2018 about GraphQL? Well, I think we did the right thing by starting simple, not trying to like come up with a grand solution that would solve all of our problems, but just start and build something small and figure out what more we needed later. We were building out a lot of schema early on, sort of speculatively, either because it was something that was in our REST API, or we even had like plans to build products that would use something like that, and we ended up throwing a lot of that away. It's so easy to like add things into GraphQL because you just add a field and it's there, and you add a resolver and it's there, and there's no like versioning or other things you have to worry about. So it works super well with a continuous delivery model where as soon as you need something, you add it, and you don't worry about sort of figuring that all out beforehand. GraphQL's structure, has a lot of opinions about types and like fields versus resolvers and queries and all this thing, can make automation work super well. We've seen some of those tools already, but it's easy to figure out if your schema is going to break. We've written our own tools, but I wish we had the GitHub thing before. And humans can easily describe things in the schema definition language. We can pull that in. We can leverage that part of GraphQL. And the self-documentation is super awesome. So like early on, we even implemented a rule that every time you add a new field, it has to have a description or it won't pass CI. So now we have this wonderfully documented schema that our clients can just look through and figure out what they need. Semantic scalar types. So GraphQL gives us like custom types that we can use. And attaching things to those, even if we don't expect them to look necessarily different from just like a regular string or something like that, gives us other benefits. Like we can validate them in different ways. We can even do non-functional behavior. So for instance, if we have a password type, even though it's just a string, we know that we can look for that type and handle it a little bit more sensitively than we would just any other user data. One of the most common reasons that we've needed to deprecate fields or remove them entirely is because we ambitiously marked them as non-null, but there was some like gamma ray that came down from the sky and prevented that field from being resolved, and now clients can't access the fields that they actually did need because of this field that they don't really need. So like every object is probably going to have a resolver. Make it null. This is the GraphQL default for a very good reason, and more and more we're shying away from adding those kinds of fields. Now, we don't talk to any databases directly through GraphQL, so this is like, oh, okay, well, we can't like write queries that have database optimizations, and isn't that not so great? But in fact, having that makes it a lot simpler to manage. It's going to be that GraphQL is kind of in the hot path of all of your clients' API requests, so you don't want to put anything in it that makes it slow, that makes it blocking, that makes it like take a lock on something. So let other services do the heavy lifting. If you just kind of like fire off requests, get them going, wait for them to come back, that scales better than trying to like figure out the perfect query pattern that you're going to be sending out before you send it, because your GraphQL server can't be doing other things at the same time. Now, the tendency, especially for backend teams, is to try to like lock everything down, right? Because we're used to this world of an API that's managed by the server, the request and the response is this like defined payload. And we want to optimize those queries as much as possible. But there's a lot more in a GraphQL world where clients are going to make their own queries, and we don't necessarily know what they're going to look like. So if you're just focusing on specific things, you're kind of losing the key advantage of GraphQL. If you use tools and patterns that kind of make everything better together, like that kind of partial query caching, or using data loader, which for us maps well to how our RPCs work, you can turn things like a single request or a series of single requests, no matter what kind of query they're coming from, into something that works a lot more performantly. And GraphQL is providing client and server a place to kind of meet in the middle, where hopefully they're not fighting out too much. But the differences are actually going to be written in code, and everybody can see them. And that's a good thing. So service engineers can see where clients are having a tough time fetching data. Client engineers can figure out like maybe where they can fetch some of that data themselves. And that resolver layer serves as not just like, here's visible on the page exactly what we're doing, but there's no two-sided interface there that has to stay in sync all the time. So we can evolve it to fix bugs, to improve performance, to improve logic, which is a huge asset when you want your clients and servers to be able to talk to each other. So at the end of the day, we started a year ago with some mounting performance problems, inconsistent response formats, a lot of different API versions that we had to maintain, this sort of difficult sequential development flow that was really slowing us down, and we maybe didn't even realize it could be better, and kind of not super clear path forward to how we're going to solve these issues. But with GraphQL, we can do prototyping with our schema. We can use our type guarantees so clients know exactly what they're getting. We can focus on building better services instead of just building better JSON payloads. We can collaborate across the engineering organization on the API so that everybody has a voice and we can build better APIs together. And it cleanly addresses client and server needs separately in the layered approach where we have schema that's doing what the client needs, and we have our services and our transports which are handling what the backend services need to do. It's way easier for us now to integrate new services and features, and you can do it too. So there are some challenges along the way, but if you stick to a few basic things, it'll help you succeed. Just start off simple, get something working, get a feel for how it does. You can always optimize later. There's tons of great stuff that you can add in the GraphQL ecosystem. If you integrate it with your existing infrastructure, then you're right off the bat going to understand how it works, not just as a toy or not just as a demo, but really in production or live with your application. If you embrace that GraphQL workflow of doing schema first and having development follow, you'll get a lot of productivity benefits. And just iterate as you need. Like, don't try to solve the world up front. When you need something, implement it. Of course, just measure everything you're doing so you know where to improve. If you're using Apollo engine and you can see kind of these are our slowest things, this is what we should focus on, that's time much better spent than tackling theoretical problems. So if you're interested in helping us solve technical problems or you know anybody who is, we're interested in solving our country's civic problems, so we have open positions on engineering teams. Feel free to reach out about those. I also hope you found something useful in this that can apply to your own experience with GraphQL. I'll be around during the break and throughout the day, so if you want to talk to me about any of this stuff, I would love to chat more. You can also find me on the Apollo Slack or on GitHub, and I'll post these slides in the coming days if you want to review anything. So thanks.